I defined acceleration, the rate at which the velocity of objects change. And I kicked it around a bit and did some examples. We'll be solving even more problems in the future. Acceleration is the rate of change of velocity. That's our official physics definition of it. Another way we could say that is changes in motion. My equations, v is equal to v naught plus at and x is equal to x naught plus v sub t plus 1/2 at squared, describe precisely, numerically, how the motion of objects change. I have a complete description of that. I can describe how the position velocity of objects change using those two equations. I can describe how they change. I'm going to shift my interest now to why do they change the way they do. If a thing is going to accelerate, why does it accelerate? What is the cause? It's a little bit tricky to teach this because you already know that when there is some sort of influence in the universe that can cause the change in the motion of an object, we usually give it a name. For example, when I drop a marker, the name that we give for that phenomenon that causes the acceleration is gravity. We give it a name. Well, it turns out that often just to have a name for something doesn't tell you much about it. So we want to dig deeper into this and see if we can discover in our universe what are the natural constraints or conditions that can cause the alteration of motion. Saying that sentence more simply, what is the cause of acceleration? It's an ancient question. This guy here, marble statue and all, is Aristotle. So we're like 400, 300 years before the Common Era. Aristotle, ancient dude. And I bring Aristotle up because he's one of the first official thinkers to wonder about this idea. What is the cause of change in motion? And the interesting thing about Aristotle is that he got it wrong. The first idea that the human race ever had about changing motion of objects was the wrong idea. Aristotle's idea was this one. Warning, wrong idea. Aristotle's idea was this, that every object in the universe exists, like my water bottle here, exists in a natural state of rest. Everything wants to be at rest. And if you're lazy, you might agree with that. And that things will only change their motion when there is some influence that is the cause of the change of motion. That is, in order for my water bottle here to move, I would have to, for example, put my hands on it and push. And when I push on it, it moves. But look, when I remove my hand, it stops moving. So the idea is that it is my hand that is the cause of the alteration of motion. But then immediately the thing comes to rest. And that was Aristotle's idea. In fact, for a long time, this was called Aristotelian physics. The natural state of everything is to be at rest. Now, I don't really blame Aristotle for having the wrong idea, because when Aristotle looked around at the world, what he realized was that everything eventually came to rest. If you throw something, it skids across the ground and it comes to rest. If you drop a thing, it hits the ground, eventually it comes to rest. Even biological organisms, animated in their lifetimes, eventually die and come to rest. It's not an absurd conclusion to draw, but it has a remarkable flaw in it. And the flaw was actually proposed to him by a student. The flaw was this. The student might say to Aristotle, okay, I understand that in order to change the motion of an object, there must be some influence that is the cause of the change in motion. And so when I take an arrow and I knock the arrow onto a bow and I draw it back, I understand, Aristotle, that it is the influence of the bowstring that is the cause of the motion of the arrow. Here's my problem, Aristotle. As the arrow flies through the air, it is in motion despite the fact that it has left the bowstring a long time ago. The influence is gone, and yet the motion persists. Now, Aristotle has to explain this as a scientist in the context of the observed behavior. So he says something ridiculous. Aristotle proposed that the reason why the arrow continues to fly is that the air in front of the arrow goes around to the back of the arrow and pushes. First of all, not a very scientific idea, because how are you going to do an experiment to prove that? I'm not terribly sure. You'd need a lot of modern technology to even try to prove that. But it's a bit silly. It sounds kind of complicated. There's a maxim that you may encounter from time to time, that the simplest answer is probably the correct one. And it turns out to be true almost always in science, in the history of science, that when our ideas start becoming more and more complicated and sophisticated to explain the universe, that's how we know they're wrong. The true ideas about the way the universe behaves are usually ones that are simple. And Aristotle was wrong about this, and so the human race was wrong about this for about 2,000 years. It was believed that the natural state of motion was rest. And it wasn't until Galileo. There's a long pace of time between Aristotle and Galileo. If you're Aristotle, you get a marble statue made, and if you're Galileo, you get an oil painting. Galileo was smarty pants. I like to tell students this little story interspersed in. I mentioned that I built a big pendulum for measuring the acceleration due to gravity. Galileo was really one of the first ones to appreciate the nature of pendulum motion. He sat in a church and watched in the cathedral the oil lanterns swinging back and forth, and he used his pulse as a stopwatch. He realized from that the equation, the mathematical relationship that exists between the time it takes a pendulum to swing and the length of the pendulum, with the acceleration due to gravity being a constant in that equation. He worked all of that out. Here's the fun punchline to the story. Galileo was 17 years old. I know in this oil painting, Galileo looks like an old dude. Well, in order to get an oil painting made of yourself, you have to be famous in the first place. In order to be famous, you have to do stuff. You do stuff when you're young, like yourselves, and then you become famous when you're old, like me. Galileo is chiefly the one who solved this problem that we have. Galileo demonstrated that Aristotle's assertions were wrong. This happened around the 1500s. What Galileo discovered is that objects of different weights fall to the ground at the same time in absence of air resistance, that the weight of a thing didn't matter, and that a moving object needs no force to keep it moving, like the arrow keeps on going. Now, there's a famous idea here with the Leaning Tower of Pisa, and here in this cartoon we see supposedly Galileo at the top of the Leaning Tower dropping objects of different weights, and the audience down here at the bottom discovering that they hit the ground at the same time. And while it's true that Galileo did that experiment, my chief interest is an experiment that Galileo did with ramps. Now, I'm not going to draw it exactly the way Galileo did, because I don't need all of the details of the experiment. I just need the idea. I want you to imagine that I make a ramp in the shape of a parabola like this, you see. And the idea, and it doesn't have to be a parabola, it's not a math thing, it's just a curvy shape that to me and to you kind of looks like a parabola. And the idea here is that I'll take a marble and place it here at the top, and it'll roll down, and it'll roll up the other side to the same height that it was released from. That was Galileo's observation. That if you release it from a particular height, it'll roll down and come to the same height that it was released from. Now, I hope that in the back of your mind you're like, is that really true? Does that happen? And the answer is no, it doesn't. The fact of the matter is, and if you, as a small person, you were given toys to play with, and you knocked things around and dropped them, and maybe you had those little cars that run through tracks and saw their behavior, you might suspect that what would happen in the experiment is that if you released it from here, it would go up and it would nearly reach the top, but it never quite reaches the top. That's going to be an issue that we investigate, but Galileo understood it. Galileo appreciated that between the marble and the track, there was some kind of interaction. The interaction that today we call friction. There was some kind of interaction that would sort of remove some of the motion before it quite got where it was going. And using his imagination, Galileo supposed that if you could remove that frictive interaction from the track, that when it went down, it would go up to the same height from which it was released. But the next discovery is the really impressive one. Galileo discovered that if you take that second ramp there and you recline it, decline it, however you want to say. You see, I've changed the shape of it. That if you release the marble from here, it goes down and will once again rise to the same height from which it was released, despite the fact that in order to do so, it has to travel a greater distance in a longer period of time. Using your imagination, you might agree with Galileo that it seems as though the marble is trying to get back to its former height. That no matter what else happens, the sole objective of the motion is to return to the former height. And indeed, if you recline it even further, it tries to get to its former height. It's always trying to use its oomph to get back to where it was. Now here is the intellectual leap. Here's the brilliance, and if you like, this is the genius of Galileo. He then imagines what happens if I recline this ramp so far that it is in fact flat. And then I put the marble here at the dotted line, I let it go, and it goes, and it rolls, and it rolls, and it rolls, and it rolls. I know that if you did this in real life, eventually it would roll and it would slow down and stop. But we're going to, in our minds, remove that frictive interaction and imagine that that marble is striving to get back to its former height, and it can never get there. The logical consequence, then, is that it will roll forever at constant velocity. Aristotle had asserted that it's the natural tendency of objects to remain at rest. Galileo discovered through experiment that instead, it's the natural tendency of objects to move at constant velocity. That idea of Galileo's is still true and accepted today in the physics that we're studying in this class. It's the natural tendency of objects to move with constant velocity. Every object in the universe has imbued within it a natural tendency to maintain constant velocity. Now, constant velocity really means two things. If I'm at rest, I have a constant velocity. And if I'm moving along at 5 meters per second and my 5 meters per second never changes, I have a constant velocity. So constant velocity can really mean two things, at rest or at constant velocity. Sometimes, not in this class, but sometimes folks say this law as an object at rest will remain at rest, an object in motion will remain in motion unless I blah, 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 blah. Lots of words and words. Let's shorten that down, have a more compact idea. It's the natural tendency of objects to move with constant velocity. So Galileo discovered that Aristotle was wrong, and it took 2,000 years for the human race to catch on to that. Well, if you remember things from your world civilization or Western civilization classes, I mean to say, we're talking about the Renaissance period, a real scientific period of human endeavor. Galileo makes this discovery, and then the next one is made, and the next one is made in a very short period of time. Human science advances very quickly. Well, in this case, the next person in line is Sir Isaac Newton, another oil painting guy. If you're not familiar, I think everyone above a certain age is aware of the name Isaac Newton, even if you're not aware of the accomplishments. There's a lot to say about Isaac Newton, but we like to keep these discussions brief, so I'll say this. Sir Isaac Newton, one of the most important human beings who ever lived, and quite possibly, although subject to interpretation, the most intelligent human being who ever lived. In his lifetime, he advanced human science in ways that for his age, no other human being would have been capable. And today, there are things that Isaac Newton put down that we still don't understand that well. The science that you learn here in this class is all down to Isaac Newton. Since his time, we've just been perfecting it and working on the details. But he laid it all out for us. And as a matter of fact, he did most of the work in one summer. They had themselves a big plague in Europe, and he went off into the countryside for the summer and did basically all the physics we're going to study in this course. He invented it. Well, Isaac Newton, of course, was aware of Galileo's idea, the nature of motion. And so he used that idea when he wrote his very famous 3 laws. Isaac Newton's 3 laws of nature are the laws that this course is based on, and that much of human physics is in fact based on to this day. We branched out a bit since then. We learned a lot of interesting things at the end of the 1800s and the beginning of the 1900s. But Isaac Newton gives us 3 laws. We're going to study all 3 of them. But today, my chief interest is the first law. Isaac Newton would have written the first law down in Latin. I wanted to give you the closest translation I could possibly give you to what Isaac Newton actually said. Of course, you're not going to read the Latin, but this is Newton's first law translated from the Latin as closely as we can. Everybody, not everybody, everybody, every physical object in the universe. So every person, every soccer ball, every car, every airplane, every satellite, every star in the sky, everybody in the universe perseveres. Sometimes they tell you to try to persevere, to keep going. That's what that word means, right? Perseverance means to keep going. Everybody perseveres in its state of rest, so not moving, with a velocity of 0, or of uniform motion in a right line. What the heck does that second sentence mean? It just means constant velocity. In our modern language, in our course, we would simply say constant velocity. Unless, that unless was always going to be there, because the fact of the matter is motions do change. Things that are at rest don't necessarily stay at rest, and things that are moving with a velocity don't keep that velocity forever, unless compelled to change that motion by forces impressed thereon. Now, if you go to different physics books or talk to different physics teachers, you might get slightly different interpretations of what this law means. I am your teacher, and therefore you get my interpretation of what it means. And of course, I'm right. Newton's first law restates what Galileo said. Constant velocity is the name of the game. But Newton's first law also defines a new physics term for me: forces, the word force. And as a teacher of this class and all the physics classes that I teach, up to this point in all the lessons, I try to avoid using the word force. Force is a common term, isn't it? You already knew the word force. It's not a new one to you. We use it in everyday language all the time. But I try to avoid using the word force. Before this moment in time, I said influence, effect, jauge. I think I even said jauge once. I avoided saying the word force because this is the definition of force. It is the natural tendency of things in the universe to move with constant velocity. And when they don't move with constant velocity, because it's just their natural tendency, when they don't move with constant velocity, there must be some natural constraint or condition that is the cause of the alteration of motion. For example, if I hold up my marker and I drop it, it does not move with constant velocity. It accelerates. There's got to be something that is the cause, Isaac Newton tells me. And everybody in the room knows that that cause has the name gravity. Gravity is the cause. Gravity is a force. In our universe, this physics is a bit fancy here that I'm doing on this slide. This isn't everyday physics. This is cutting edge physics. But since Newton made this revelation about force, we've gone around the universe looking for forces. And we have discovered that so far as we can tell today, it's pretty exciting because I'm willing to admit that 100 years from now, this list might be different. And within the last 200 years, this list has certainly changed. But as of today, there are only 4 forces in the universe. Only 4. The first one, they're listed here in terms of scale. Gravity's on a big scale because it's all planets and galaxies and stuff, right? Sure, it's the reason why my marker falls, but it's also the reason that the Earth moves in orbit about the sun. Gravity, very familiar. Everybody knows about that one. Electrodynamic. That's electricity and magnetism together. There was a time in human history, not terribly long ago, where it was thought that electricity and magnetism were 2 different things. Since then, we've discovered that electricity and magnetism are the same thing. And that electrical force, the electrical force that holds atoms together, and the electrical force that holds magnets to the fridge, which is a magnetic force, those are the electrodynamic forces. The next 2 on my list, it would not surprise me at all if you'd never heard of. But a thing that you learned in chemistry is that the nucleus of an atom is composed of positively charged particles called protons. Those proton particles strongly repel each other. Any 2 protons near each other exert an incredible amount of force one upon the other. Electrodynamic force. So it seems as though the nuclei of atoms should just explode and blast apart. But they don't. They stay stuck together like that. And so the physicist looks at that and says, wow, there must be some force that is holding the nucleus together. And the physicist standing next to that physicist says, well, it would have to be awfully strong. And so we call it the strong force. The strong force is quite literally the force that holds the nucleus of atoms together. There's another very, very strong force that holds the protons together. I don't want this discussion to get away from us. Maybe you heard a rumor that protons are made of smaller parts called quarks. A proton actually has 3 parts inside of it. They're called the quarks, 2 ups and a down. What? Yeah, the physics gets fancy really quick. There's a force that holds the quarks together. That force is damn strong. But it's not as strong as the strong force, so we call it the weak force. These 2 forces, the strong and the weak, we're not going to worry about those because they happen inside the nucleus of atoms. And our physics is not going to go that far. But there are 4 fundamental forces of the universe. If I think about it this way, then physics is not very useful to you, the student in this class. So instead of thinking of the fundamental forces of nature, let's instead think about everyday forces. Influences that we've identified that can cause changes in motion. If it can cause a change in motion, Isaac Newton assures me that is what I mean by force. And I said gravity because everybody knows gravity, it's the obvious one, but look at all these others that you know about. Weight is the force of gravity. The force of gravity and the weight force are the same force. Different name for the same thing. But you can push on a thing and change its motion. A person can push on a crate and cause its motion to change. You can pull on a thing, grab a shopping cart by a handle and pull it down the aisle. Tension is specifically the force exerted by a rope. You can tie a rope to a thing and change its motion by pulling on a rope. That's called tension. Contact forces, really push and pull are contact forces. What I mean by contact force is when I lean against the board, there's a force of touching. The touching force, I call a contact force, and it has another strange name called the normal force. But we'll come to that a little later on, understand why that force is not so strange. Friction force, when things rub together, it affects the motion. Everyone, I think, is aware that friction exists. Well, we're going to understand it. We're actually going to understand it mathematically in our course. Air resistance, we know that's a thing. The thrust of rockets, buoyancy, things float in water. Electric forces and magnetic forces, like the forces that hold together atoms, or magnets and those forces. These are sort of everyday forces. These are the kind of forces that I, a teacher of physics, can write problems about. Guy pushes on a crate. Rocket has so much thrust. A rope is pulled with this much tension. And we recognize that there are these things in everyday life that are constraints or conditions that can cause the change in motion of a thing, and we call those forces. And it's possible that we'll encounter all of these as we investigate the kinds of problems and investigations that we do in physics classes. Now, a thing that Isaac Newton understood that we're going to get into a bit more in our next discussion was that in any given situation, there could be more than one force that acts. There could be more than one force that causes the alteration of motion. For example, as I stand here in front of you, I'm in contact with the floor. The floor is pushing up on me. Gravity is pulling downward on me. There's more than one force. And if you're involved in something athletic or a machine that has many parts, there could be very many forces involved. The net force is the sum of all the forces. The thing is force. Like position, displacement, velocity, and acceleration, force is a vector quantity. It not only has an amount, but it also has a direction. Now this slide jumps the gun a little bit because it has the units of force on it. Forces are measured in newtons. The capital N here stands for newtons of force. We're going to get into those units next time. It's just that you can't write down a scientific quantity without including the units. And so when I say a force of 5, I have to say 5 newtons. Of course we named the unit of force after Isaac Newton himself. You may be thinking in your head, yeah, Shadi, but my weight is in pounds. The pound is a unit of force, but it's the imperial unit of force, not the metric unit of force, certainly not the SI unit of force. The SI unit of force is the Newton of force. So here in this example, I have 2 5 Newton forces pulling in the same direction. So here's 2 5 Newton forces, and I've represented them with arrows because there's a difference between pulling to the right and pulling to the left. And as I've drawn it here, the 2 5 Newton forces are pulling to the right. The net force is the combined effect of those 2 forces. But since they point in the same direction, their combined effect is 10 newtons. 2 5 Newton forces to the right is equivalent to 10 newtons. Well, Charlie, that's just addition. That's not even hard to do. Hang on. If I have the same 5 Newton forces, but they point in opposite directions, it's not simple addition. It's not 5 plus 5 is 10. Because they point in opposite directions, and you can think about it as math, but also think of it as oomph, zhuzh, influence. If the 5 newtons pull in opposite directions, the sum total of that influence is 0. Very often when this happens, we like to say the languages, they cancel out because one is directed to the right and one is directed to the left, and they are equal. The sum total of those forces is equal to 0. The point of this observation is that force is a vector, not only how many newtons, but in what direction, and the direction matters. And it can get, admittedly, a little bit complicated. Here I have a block and there are 2 forces acting on it. There's a 30 Newton force directed towards the top of the screen, and there's a 40 Newton force directed to the right. Well, how do you add up forces when they're at right angles to each other? Because I can't just add them and I can't just subtract them. The sum of these forces isn't 40 plus 30. The sum of these forces isn't 40 minus 30. It's actually determined by the Pythagorean theorem. Now, I know that's taking our math to a new level. It's not going to happen often. But when we have these sort of right triangle things, we're going to have to appreciate that the total force is not upward or to the right, but instead is diagonal. 30 newtons squared plus 40 newtons squared, square root, is 50 newtons. When forces are at right angles to each other, they add according to the Pythagorean theorem. So when forces are in the same direction, they add. When forces are in opposite directions, they subtract. And when forces are at right angles to each other, they add according to the Pythagorean theorem, which I hope we're very familiar with. For starters, I want to consider situations where all the forces add up to 0. One force cannot add up to 0. In order to get your forces to add up to 0, you need many forces. When all of the forces add up to 0, that condition is called equilibrium. The term equilibrium specifically refers to a situation where the sum total of all forces present, added as vectors, is 0. Here's a quick equation, or a quick example, I should say here, this notation stands for all of those words. This funny looking symbol here, I hope you recognize, is a Greek letter capital sigma. In mathematics, the capital sigma stands for sum. So how I read this equation is the sum of the forces equals 0. Once again, using an equation as shorthand for lots and lots of words. When the sum of the forces is 0. So here's my example. There are these painters, and for fun, they're painting a sign that says sigma f equals 0. Good times. They're standing on a platform that's suspended by 2 ropes. And they have one painter over here, and he's standing over here, and he has some weight. And there's another painter walking along here on the right, and he has some weight. And then there's the weight of the platform itself acting downward. But the whole thing is not accelerating. Good news for the painters, because if you're standing on a platform next to a building very high above the ground, you do not want to accelerate. Acceleration bad. You want to stay put. In order for them to stay put, the sum of all the forces has to be equal to 0. And as you can see, that can happen, because the rope force on the left and the rope force on the right point upward. And that's a certain number of newtons. Just for giggles, let me say that's, 800 newtons of force. I just made that up. So it's 800 newtons of force upward. But then you have the weight of the 2 painters downward. Let's say each painter has a weight of 200 newtons. So then that's 200 and 200 is 400. The weight of the platform must be 400, so that there's 800 downward and 800 upward. Because the acceleration is 0, the sum of all the forces must be equal to 0. The force upward must be equal to the force downward. A newton is smaller than a pound. It's frightening, but I'll tell you that I weigh about 1,250 newtons. It's 4.45, I think, newtons per pound. I regret that I just said that out loud in a recording that's going to go on the internet, so I could be wrong on the internet. You know what? I'm probably right. I'll look it up after the fact, and if I'm right, I'll leave it in the video, and if I'm wrong, then I'll edit it out. 4.45. So the arrows represent the force vectors, and the sum of the upward forces minus the sum of the bottom forces equals 0. The forces cancel to 0, and the system is in equilibrium. You might think, oh, I get it. It's in equilibrium when it's not moving. That's not true. Because an object can be moving and be in equilibrium. Because remember, Galileo discovered, and Newton reasserted, that it's the natural tendency of things to move at constant velocity. If you move along at constant velocity, your acceleration is 0. And you're in equilibrium. And the total force on you must be equal to 0. And you argue, no, you have to, for the crate to go along, see the cartoon fella here pushing on a crate. In order for the crate to go along, you have to push it. Yeah, but there's an unseen force there. The crate is rubbing against the floor and creating a friction force that opposes. When the crate moves at constant velocity, the acceleration is 0 and the push force is equal to the friction force, so that the net force is equal to 0 and the crate does not accelerate. Now, this fellow could increase his force. If he does, his force starts to win, sum is not 0, would accelerate. This fellow could reduce his force. If he does, friction starts to win and it accelerates. In one case, the crate will speed up. In the other case, it'll slow down. I would really like to be able to calculate how much acceleration I get when the forces aren't in equilibrium. And that's the subject of Isaac Newton's second law, which we will investigate next time.